At an air show, a small aerobatic plane rolls onto its back and keeps flying, straight and level, a few hundred feet over the crowd, upside down. The wing is carrying the same weight it carried a moment earlier. The only thing that has changed is which way it's pointed. The curved upper surface that almost every explanation of flight treats as the source of lift is now facing the grass. By the theory most of us were taught, that shouldn't be possible. If a wing flies because its rounded top makes the air rush faster over a longer path, then turning the wing upside down should aim that force straight at the ground and drop the airplane out of the sky. The pilot isn't concerned. He holds the inverted line as long as he wants, rolls upright, and lands. So either the pilot is suspending the laws of physics for the afternoon, or the explanation in the textbook was never the reason that wing worked. It's the second one, and most of the people who taught you the first one were never told that themselves. The version almost everyone learns goes like this. A wing is shaped so the top is curved and the bottom is nearly flat, which makes the upper surface longer than the lower one. Air arriving at the front splits, some going over the top, some passing underneath. Those two streams, the story goes, have to meet again at the trailing edge at the same instant. The air on top has farther to travel in the same time, so it has to move faster. Faster air, by Bernoulli's principle, means lower pressure. Higher pressure below, lower pressure above, and the wing gets pushed up. It's worth sitting with how reasonable that sounds. Every piece of it is something you can picture. The shape is real. Bernoulli's principle is real and correct. And once you accept the setup, it's clean enough to draw. Two little dots racing along the surfaces to meet at the back. That diagram is in physics textbooks, in pilot ground school manuals, on the placards under museum aircraft. It's been taught for the better part of a century. It didn't survive because nobody checked. It survived because it's satisfying the way a correct explanation is supposed to be. It hands you a cause and a clean result you can almost feel. The only trouble is the one sentence the whole thing rests on, the part where the two streams have to meet at the back. So someone went and checked whether they actually do. Put a real wing in a wind tunnel, add smoke so the streamlines show, and tag the air as it splits at the leading edge. The two tags don't meet at the back. The air going over the top reaches the trailing edge well ahead of the air underneath, which arrives late. There was never a rule that forced them to rejoin. Someone assumed it, drew it, and the picture stuck. That by itself ends the theory, and it gets worse from there. Work out how much faster the longer path would force the top air to move just to meet the bottom flow at the back. Then measure the air over a real wing. It's faster than that catch-up figure, faster than the theory even asks for. The air isn't straining to keep up with anything. It's already outrunning the one job the theory invented for it. And the speed difference the longer path can honestly explain, fed through Bernoulli, predicts a fraction of the lift the wing really makes. An airliner trusting that figure would never leave the ground, and it can't account for the wings that plainly do fly. A flat sheet of balsa thrown at the right angle lifts, and its top and bottom are the same flat length. A folded paper airplane has no curved top at all. The cleanest case is the one already in this video. An aerobatic wing built symmetric on purpose, top and bottom a matched curve, the path over each side identical to the millimeter. By the longer path theory, it should make no lift at all in either direction. Instead, it flies just as well inverted. If lift came from the top being longer than the bottom, none of these would leave the ground. which leaves the question the smoke already raised and didn't answer. If the air over the top isn't hurrying to catch up with anything, why does it speed up at all? Start with what the wing does to the air, not what the air does to itself. A wing moving through the sky takes a large mass of air and turns it downward. You can watch the wake spill off the back of an airliner on a damp morning and sink. The wing is throwing air toward the ground, steadily, by the ton. Air has mass, and shoving mass in one direction takes force. When the wing drives that air down, the air drives back on the wing with an equal force pointed up. It's Newton's third law, the same trade a swimmer makes pushing water behind her, or a rocket makes throwing its exhaust down to climb. The wing holds the airplane up by throwing air the other way. How hard it throws the air comes down mostly to one thing: the angle between the wing and the oncoming flow. Raise the leading edge a few degrees, and the wing turns more air, more sharply, and the upward force grows. That angle, not the curve of the top, is the lever the pilot actually holds. It's why a flat plate flies, and why easing back on the stick raises the nose. And it answers the airplane we opened with. Upside down, the curved surface does the pilot no favors, but the angle still works. He eases the stick forward, setting the inverted wing to drive air toward the ground, the way any wing does, and the air drives back the other way, lifting the wing toward the sky and holding him level. The shape was never what kept him up. The air he could throw was. That still leaves the smoke trails question: why the air over the top speeds up if it isn't racing anyone? The answer is in the shape of its path. The air over the top doesn't travel in a straight line. It clings to the curve of the wing. Peeling away would tear a near-empty gap behind it, and the surrounding air pressure won't allow that. So the flow stays pinned to the surface and follows it down past the trailing edge. It holds like that right up until you tilt the wing too far and the flow finally lets go of the surface. That's a stall. Bending a moving flow takes a sideways difference in pressure, lower on the inside of the bend. Over the top of the wing, the inside of that bend is the surface itself, so the curving air pulls the pressure down right against the wing. That low pressure is the lift, and that same low pressure is what pulls the air over the top faster. The speed up was never the cause of anything. It was the fingerprint of the pressure drop already doing the work. For the engineers in the audience, the sharp trailing edge sets how strongly the wing circulates the air around itself. That's the Kutta condition, and that circulation is what sets the lift. So, was Bernoulli wrong? No. Everything Bernoulli's principle says about the wing holds up. The air over the top moves faster, and where it speeds up, the pressure falls. That pressure drop is part of what holds the airplane in the sky. Bernoulli was never the myth. The myth was the reason offered for the speed up. The story about two streams hurrying to meet at the back. And here's the part almost nobody says out loud. The pressure account and the Newton account aren't two separate forces stacked on top of each other. They're one lift, written down twice. The low pressure above the wing and the air thrown downward off it are the same event. The wing can only pull air down by leaving low pressure above itself, and that low pressure is exactly what bends the air down. Add up the pressure over every inch of the wing's skin, and you get a number. Measure the downward momentum the wing hands the air each second, and you get the same number. Two ledgers, one force. That's what makes the textbook version such a strange failure. There was always a clean, correct way to describe a wing sitting right next to the broken one. It just wasn't the version with the two little dots. So go back to the airplane on its back over the crowd. Nothing about it was ever strange. The wing was throwing air toward the ground the whole time, even with the ground above it, and the air was throwing the wing the other way. The shape of the top helped a little and explained almost nothing. What kept that pilot in the sky was the same plain bargain that holds up every wing ever built. Push the air one way, get pushed the other. And the same air holding that wing up is pulling on it too, bending it, trying to fold it back over the fuselage. On a smooth day, you would never feel it. In rough air, the loads climb high enough to tear the wing clean off the airplane, and they almost never do. That is a different account, and it is the one worth telling next.